Those don't know, Jeremy is an assistant professor at the Chesapeake Biological Lab. He studied under Walt Boynton and Mike Kemp.
The other way around.
Mike Kemp and Walter
It sounds
Boynton.
better, his one.
Yeah, and both masters and PhD, and then did his undergrad, where was that, Rochester?
Syracuse.
Syracuse, all that upstate New York stuff.
ESF, that's right.
He also did a little, his little personal mini sabbatical in Australia, and he married up, and his wife is
Don't we all?
a part-time Ian employee. She's responsible for our Ian report card, among other things. So we're glad that he could make the time today to come up here to get this on film.
Well, thank you. I'm Jeremy Testa, and today I'm going to be walking through a presentation that summarizes this synthesis and review we did of Chesapeake Bay hypoxia forecasts. The forecasting effort has been going on for about 10 years now by a host of different characters, and we convened a class in our graduate program in an effort to review that forecasting experience, see how well the forecasting did, and understand what the impact of the forecasts were. So this author list here represents the group, which included myself and Bill Dennison as teachers, our colleague Don Scavia from the University of Michigan, and a number of graduate students within our program. So as such, it was a multi-institutional effort, certainly within the team in our class, which represented a number of people from UMCES, but also people from various parts of the University of Maryland system, both extension and some of the other campuses around the state. It also included our colleague, as I said, from the University of Michigan. And because this was an effort that was dependent upon data collected by a number of agencies, we really had a number of partners from Maryland DNR and the EPA collecting data. USGS has been really key in providing the loading that we use. NOAA has provided funding for this and support, and there's been a number of forecasters that came in and out of scene over the years, and really I'm kind of the most recent player. So I'm a little bit of a Johnny-come-lately, but I came in at the right time. So here's a quick overview of what I want to cover today. I want to say a little bit about the hypoxia problem, although it's a familiar problem. Talk a little bit about Chesapeake Bay hypoxia and a little bit of a history of the science related to that. Talk about forecasting hypoxia, both why we do that and can it be done and what we might learn from that. So that's this last bullet. What's the impact of that hypoxia forecast? And then do a little bit of looking ahead, and really in the context of this talk that will address the forecast from this summer and some of the deviation from that. So as well, we're kind of reviewing a paper that came out of this class in bioscience this spring that highlights this work. So ecological forecasting has been a growing thing within the scientific community. So the number of publications that sort of address some sort of ecological forecast or prediction has really been on the rise. So as our understanding has gotten better and the data have gotten better and more voluminous, I guess, the ability to forecast has gone up. And it's also true that forecasting gets better with age. So the more times one goes through the experience of forecasting, the more data is collected, and a refinement of these forecast models, whether they be mechanistic or statistical, gets better. So this is a plot of NOAA weather forecast skill over the last 60 or 70 years. And you can see that it's gone from when my grandfather was young, 25%, to when I was in college, up towards 80. So just thinking of how generations perceive weather forecasts is related to something like this. So moving on towards the problem of hypoxia, it's a fairly recognized problem in the estuarine realm. And this is a figure from a well-known paper by Bob Diaz and Rucker Rosenberg, where they looked at reports of hypoxia across the globe, and in this figure they link them to some impact of human impact on the land. And so the reds in indicate really high human impact, and the black circles represent where there's been hypoxia reported. And it's no surprise that where you have a lot of red in impact, you have hypoxia. And it sort of summarizes our general understanding that where you have human impact and you have nutrient inputs, you tend to have this condition of low oxygen, which I'll get back to. And looking over time, the reports of hypoxia have historically been on the rise. So there's a number of reasons why that happens, in part because human impact on the land has increased. Now, hypoxia is an interesting problem scientifically for a number of reasons, but also for sort of an estuarine water quality management perspective. And so this is a figure that kind of represents a lot of the different processes that both cause and control oxygen, but also the negative impacts of hypoxia. So scientifically, it's interesting for a number of reasons. So first, oxygen varies on a lot of different timescales, and all those timescales are important. So oxygen goes up and down over the course of the day with photosynthesis during the day and respiration at night. It varies on the timescale of days to weeks with events. It seasonally varies strongly with temperature and changes in stratification. And we also know there's a lot of interannual variation. So there's a lot of timescales that are important. Another reason why this tends to be important, and I kind of like to refer to oxygen as a keystone molecule in these environments, it's really important for habitat because most of sort of the higher organisms that we're concerned with can't tolerate low oxygen conditions. The phenomenon or the condition of low oxygen water actually affects nitrogen and phosphorus cycling in a way that enhances their recycling and availability within the ecosystem. So the condition of low oxygen can create conditions that support more nutrient availability and subsequent further hypoxia. So it can sort of self-reinforce itself. There's a lot of anaerobic processes that happen when there's no oxygen. Some of those processes produce greenhouse gases that are important, like methane, and they can lead to the production of things like sulfide that are toxic to a lot of organisms. So oxygen sort of not only immigrates all the physical and biological and physical processes that are happening in the estuary, but it also just has an effect on pretty much everything that we think is important. So turning to Chesapeake Bay, people have been studying this problem for a long time in the system. And the time scale that we have been forecasting, that a lot of people have been forecasting, is this seasonal hypoxia. And so this figure to the left sort of shows the bathymetry of the bay, and you can see the deep channel that's in red and yellow that represents the deeper part that tends to go hypoxic. And if we look at distributions of oxygen, now looking at the bay from the side, you know, the left here is the Susquehanna River, and the right here is the Atlantic Ocean. Looking over the course of the season, we can see hypoxia develop in May and early June in the upper part of the bay, and as the summer progresses, oxygen gets lower, it moves seaward, and then it starts contracting back in the fall. And so the forecasting we're trying to do is to capture this seasonal phenomenon, and as you'll see later, we actually forecast in 3 different times of the summer to try to capture some of these different dynamics. Now, there's been a lot of work scientifically in Chesapeake Bay, and we tried to sort of review or quantify that by looking at the number of publications that sort of refer to Chesapeake hypoxia over time. That's what's represented here by these gray bars. And these words here relate some sort of key milestones in the history of the science here. And the circles and lines represent the sort of average July hypoxia over time. So you can sort of overlay the problem over the scientific response to address it. And so what comes out here, starting in the early 80s, is when sort of papers talking about Chesapeake hypoxia tended to show up. And it was about that time that the hypoxic volumes really started jumping. Now, there's no necessary cause and effect here, but it's interesting that they're coincident. So what's also interesting is that in this early part of the time frame is when sort of the pollution problem in Chesapeake Bay was really catching some heat. And there's some pretty well-known papers in the journal Science that sort of brought attention to this. that's what was happening here, and that's when the Bay Agreement began, and we started monitoring the Bay that generated this data set that was necessary to do forecasting down the line. And so as time went on, there were sort of these periods of low activity that then were sort of followed by really high increases in activity. So by the early 90s, we had enough data where the first budgets of oxygen were coming into play, where we could understand, or at least begin to understand, the interplay between physics and the biological processes. As time came on into sort of 2000s, we sort of turned the course in the century. Really long-term data sets had developed, and we could really start to understand sort of the multi-decade changes with hypoxia. And it wasn't long after that, that we started doing forecasting. And so the forecasting involved statistical models, but at the same time, the three-dimensional hydrodynamic biogeochemical models that could do much more spatially, temporally resolved simulations starting to come online at that time. So our knowledge of the problem has sort of expanded exponentially, really, and it's been really rapid in the last decade. So, why should we forecast hypoxia? There's a number of reasons why. As I said before, it's a keystone molecule for life and for a lot of processes. Hypoxia integrates the response of the system to a variety of processes, both sort of pollution issues, but also the physical forces in the system. And they kind of test our knowledge of the system in that way. There's considerable management efforts being made to reduce the eutrophication that causes this hypoxia, as many of you know. And interestingly, the statistical forecasts I'm going to talk about, one of the things we addressed is that in Chesapeake Bay, there's already a modeling system set up to understand and sort of quantify what the response will be to nutrient inputs. This is sort of a second view of that that's done at a different time scale. And finally, why forecast? There's a legacy of scientific research and bay monitoring that has really developed at this point that's allowed us to put together fairly reasonable predictive models. So this is what the forecast models have looked like over the recent decade. And this is a snapshot from the Integration Application Network's website that sort of represents this forecast. So each year in May and June, we network with our colleagues, make a prediction for three different types of forecasts, which I'll talk about in a second. The Department of Natural Resources kind of evaluates what's happening over the course of the summer. And then in the fall, we usually do a review of what happened. So were the forecasts right? And what were some of the reasons why they might be right? And in this paper, we actually sort of tried to do that in a more comprehensive way. So in Chesapeake Bay, there's three forecasts, as many people know. There's a July average hypoxia forecast, oxygen less than 2 milligrams per liter. That's kind of the summer peak period. And then we do an early summer and a late summer anoxia forecast, which is sort of operationally defined as less than 0.2 milligrams per liter, but really kind of represents zero oxygen. And we do both of these, or all three of these, because it allows us to capture sort of different parts of the season and how they're responding to various forces, and they're also allowing us to look at both very severe low oxygen conditions and then perhaps moderate or just normal low oxygen conditions. And these are statistically based models, all of which are derived with some measure of nutrient input from either just the Susquehanna River or the Susquehanna River plus the Potomac. The early summer models are really just simple regression models where the summer hypoxia model is kind of a deviation of what's called an oxygen sag model that engineers developed to look at oxygen depletion below sewage treatment plants in rivers. So we have these three forecasts. And one of the main thrusts of this effort that we did was to sort of see how well these forecasts did. And so we have three forecasts, and this is going to be the most complicated figure I show here. But what you can see, the lines, right, are the forecasts, and the dotted lines are the confidence intervals around that forecast, and the circles are what was actually observed that year. And so we're going from 2007 through to 2015. And so the bars below, the grays, the light and the dark grays, are the anoxic forecasted volumes. So let's just point out some highlights here. There were a couple years, 2007 and 2014, where the forecast just missed pretty substantially. And where they missed, the models far over predicted the hypoxia. And there's other years where the models missed, but they tended to underpredict hypoxia. So 2011 was one of those years, which was an interesting year on a number of fronts. There was really high flow, the highest July hypoxia that we really ever measured. And of course, Tropical Storm Lee came in the fall, which isn't relevant here, but it's just part of that story. So we wanted to examine why the model didn't match the data. And remember, we're making these forecasts in the spring just based on nutrient loading. Nutrient loading isn't the only control on hypoxia. So one of the things one of the students, Alex Fisher, did on our team was to relate the deviation of the forecast from the observation to the average wind direction in the summer, right? And so there's two sort of features to this figure, right? So any dot below here, there's an overprediction by the model, and any dot above, there's an underprediction. So 2014 and 2007 stand out. We just severely overpredicted hypoxia. And if you remember 2014, there was a really strong storm that came up on the 4th of July right before the monitoring happened. And in 2007 was one of the highest sort of Julys in this record for sort of sustained high winds. So when you have really strong winds, independent of the direction, it just tends to mix the water physically. And we can't predict that in the spring, but we know it's a key feature. So the other part of this is where this sort of significant regression line comes in, is that where we overpredicted, the winds tended to be from the south, and where we underpredicted, the winds were from the west. And this is consistent with what the physical oceanographers have relayed to us in recent years, that western winds tend to sort of at least enhance or sort of keep stratification kind of as high as it could be. Right, so we underpredict it when stratification tends to be higher. And the south winds really sort of mix the water column or result in a secondary circulation that results in mixing. So where you have southerly winds, we tend to overpredict because the physics take over. So in short, the models did pretty well, and where they didn't do well was associated with something that we understand and something that we really also can't predict. So the last thing we did in this project was to look at the media response to what we were doing with the forecast. And this was done using a Google News search over the past couple of decades. 2007 is where the forecasting began. And these are just a number of news articles that talk about Chesapeake Bay hypoxia. So it was clear that when the forecasting began, there was sort of an uptick in the number of news articles that were addressing this problem. And the white bars are news reports that specifically included mention of the forecast. So the media response sort of followed the response, or the activity of the forecasting, and the website that was used to display it. So what did we learn? Hypoxia forecasting in the Chesapeake has been a success, by and large, given what we can predict in the spring. But as always, there's room for improvement. Even though the statistical forecasts we do are not used in a management context specifically, they set up sort of a communication cycle that really raises public awareness of these issues. We can use these forecasts to communicate the complex ecology of the bay and just the complexity of the hypoxia problem itself. And it's worth noting that these forecast models really only were developed after decades of both research and the data streams that came together that could support them. So I just want to spend one more minute on a slide to talk about this year. So we made a forecast this spring that suggested higher than average volumes of both hypoxia and anoxia, in large part because the flow from the Susquehanna River was quite high. This figure here is the latest report from the Department of Natural Resources that shows, at least in Maryland, what's been happening this summer. And what we've seen is, although the volumes in the early part of the summer in June were average or slightly above average, as the summer's progressed, the volumes have been below average. So actually opposite what we forecast. And although I didn't have the time in preparation for this to sort of do a full assessment of why that is, this is sort of consistent with something that we've been noticing about at least Hypoxia, if not oxygen in general, over the past few decades. So just to briefly address that, this is a seasonal cycle of the anoxic volume in the bay split into the 1985 to 1999 period and the 2000 to 2015 period. And what we've seen is in the last 15 or 20 years, the volume of Hypoxia in the latter part of the summer has been going down, just like happened this year. Consistent with that is the day that Hypoxia breaks up in the waters of the bay that are sort of around the Potomac and south has been getting earlier, right? So anoxic volumes later in the summer are going down. Hypoxia is breaking up earlier. And if we look at the anoxic volume in the later part of the summer generated for a given river flow, although there's a lot of variability here and sort of the maximum is the same, you can see a slight downtick in what we're seeing. And so there's something that's seasonally dependent that's changing that we almost understand at this point. But there's a paper that we're working on to address that, so stay tuned. Thank you.